Thank you. Yeah, my name is Jonas. I'm the Director of Engineering for the audio-video organization at Discord. And what I want to talk about today is a product that we offer that's called GoLive. You might think GoLive, it's a funny name, but really what GoLive is a product we built specifically to solve the use case where you want to share gameplay with your friends. So imagine like you're watching your friend and there's like a split in the road and you're yelling like, go left, go left. The latency has to be short enough for your friend to be able to act on that while you still can see what's going on, right? So GoLive is trying to solve this specific use case for users that are like, want to be present with their friends when they're playing games. It's almost easier to show the thing we're optimizing for, so I'll just show a quick demo, and then I'll talk about sort of the things we're doing. So here we have Discord. I'll start a game here on the right. I'm starting a game called Ape Out. And as a user, we already detect that you're playing a game. So you don't need to do anything as a user. We know you're playing a game. We know what game you're playing. We know what window needs to be captured. So I just have to press stream. And that's about it. As a user, I have to do. I get a preview of the right window. We've correctly identified what resolution needs to be streamed. We correctly identified the frame rate. I press stream. And we're now sharing video with less than 1 second of latency to our friends. And this is the kind of thing that we are trying to build for. Not specifically like how do we scale to millions of people, but how do we scale millions of calls with small amount of people where they can sort of have this experience of being present with someone else on the couch. Really like the thing internally we're talking about is sort of we're trying to build FaceTime for gaming, if that makes sense. So if you don't know about Discord, if this is new to you, Discord is a communications platform that is sort of tailored to building communities around interests and specific sort of small communities. But what we do really well is gaming. We think about Discord as like the best place to connect before, during, and after people play games. And you might wonder, why is that so important? It is important because there are so many games that have different launchers, they have different publishers, they have different friend codes, and it's a mess out there. And really what we provide is a way for you to say, like, here's my friends, and I want to talk to them overnight, regardless of what game we're playing, and we sort of connect you with your friends across that entire experience. In terms of numbers, we have over 200 million monthly active users, so anything we build has to scale in like, you can think about the scaling required to sort of power that thing. Every month, our users clock over 2 billion hours of games they're playing while using Discord. And of people who use Discord, 80% of them are using our voice chat feature when they talk to each other. And 31% is using the GoLive feature I just mentioned. So there's a lot of individual small calls in the size of maybe 1 viewer or up to 10 viewers that are using this feature all the time. So why is this different, right? What makes this challenge different from something like we talked about before, like the entire day has been about how we scale broadcast? It is different. First of all, we run a client, I think like what everyone else here in the world does. We have a client for desktop, we have Windows, Android, iOS, macOS, etc. But that, I think, has become table stakes to have a client everywhere. But when I looked at the data and I thought about like what is specific about the challenge we're solving that you might not get elsewhere, it's the origination of the streams that we are dealing with. And the best way to sort of illustrate this is to look at where our streams are coming from. For us, 91% of streams are coming from a Windows device, which I think is very uncommon. If you look at this, you have 91% of Windows, and I think I can't read because I forgot my glasses, but it's 4% iOS, 3% Android, 1% Mac OS, and then there's a sliver there of the people who still think Linux is going to be a thing for desktop, but that might not happen. But I think if you look at this compared to if you're building encoding pipelines or transcoding pipelines, you're probably using Linux and you're probably using open source tools like FFmpeg. These either do not exist or does not work as well in the context that we are trying to solve for. So the challenge that we have to do is like we have to build streaming for users, but we can't use the commonly available tools that are on the market. So how do we go about doing this? And that's what I'm about to talk about today. And just like share how you can do this in Windows and the challenges you have to face. So things we're trying to solve for with Discord, like what are the constraints that we are specifically sort of honing in on? First one has to be very low latency. And I say very low latency, I'm sort of, we saw that thing that Mike just presented. What I'm talking about is in the ultra low latency range. So we want to be less than a second. Preferably should be so close that you can sort of enable that use case where you can imagine someone sitting next to you on a couch. That's how it should feel like if you're using Discord. That rules out things like LHLS. But we're not going to talk too much about that today, because it's not a secret that we use WebRTC, and we've tuned the hell out of it, but it's not enough time to cover that. So I think what I want to focus on is that to do this, you not only need to tune WebRTC, but you also need to tune encoders. Because the encoders at the end of the day is responsible for a lot of latency. Encoders can add up to seconds of latency if you don't configure them correctly. So the way you tune these encoders is super important. The second thing that we have to challenge with is that we can have no game performance impact. And when I say game performance impact, what I mean is that primarily when people are using Discord, they're playing a game. This is unlike if you're watching a TV, like if you're watching a movie, the primary thing you're doing is watching a movie, so you don't really care if the set-top box is burning up. But for us, people are playing a game, and secondary, they're sort of talking to their friends, and then third, they're trying to win the game, and then fourth, they might be sort of thinking about streaming. So if we have any performance impact, the second a user notices, they just turn off the stream. So for us to have any leverage with this, it just cannot impact the performance of the user's hardware. We need to sort of achieve a good quality, and I'm using good here on purpose, at a high frame rate. And when I say high frame rate, what I mean is, if you think about Zoom, Teams, or sort of Google Meet, when you're sharing something like this, if I were to share this presentation, the effective frame rate of this is basically less than 1. I could send you a couple of JPEGs in an email, and you get the gist of it. But that is not the case when it comes to gaming. It's very like sports in that sense, that you need the high frame rate to understand the action that is being taken. So we need to keep the frame rate high, regardless of like what we're doing here. And then lastly, our users want it for free. And you can think about how these constraints sort of work against each other, in the sense that we're trying to do all these things and users have no desire to pay for it. We do offer an upsell called Nitro that people do pay for, and that gets you from good quality to high quality. But for the good quality, we have to offer this for free. So with these constraints in mind, like how do we go about solving these? If you had asked me 10 years ago, I'd be like, it's impossible. You cannot solve these constraints without either sort of giving away the free part or getting bad quality. But there's been a development that I think you are probably all aware of it, but it's just like been so slowly boiling forward that you kind of don't know how far it's gotten. And that is the state of what we have with hardware encoders in the hands of consumers. If you think about what you have in your pocket today, you have a phone, and I will bet that your phone today probably has a better hardware encoder in terms of quality and speed than if you bought an elemental encoder 10 years ago. That's how fast we've gotten there, right? It's just advanced so fast, and that is a phone. If you have a gaming GPU, like a 400-watt GPU that you bought for $1,000 and put in your computers, these are really fast today. They can do real-time AV1 at the same time as they're doing real-time HEVC, at the same time as they're doing real-time H.264. You know, most consumers can do this in their home right now. I think that is the thing that has changed over time. So how can we leverage? I mean, basically, we have to leverage this to do things. So when I say that this is something that has changed, another thing I don't think people realize, that I've realized over working with this, is that GPUs today, they have these GPU cores that are, they're used, basically these are, I'm simplifying this a lot, but these are the cores that are used to render the game. So if you think about, like, you know, you have these worlds, they're doing the rasterization, the shading. Think about ML, for example. That is something that is being done on the GPU cores. But separately, on all modern GPUs for the last 10 years, they've also been shipping with a separate video decoder and a separate video encoder. These are separate part of the hardware die, right? If you think about the silicon that you have in your home, they have a separate part that cannot be used for doing anything but these two things. So these are sitting there doing nothing if you're not using them. So in our case, because the game is hogging the GPU cores, maximizing them, we have access to these things that are just sitting there doing nothing. So that's how we can achieve this today that we couldn't do 10 years ago, but it's possible to do today. Okay, well, we're done this, I guess. That was an easy talk. No, the problem is in a modern desktop architecture, you have another thing that you have to contend with, which is that it's not just easy that you have a GPU, you also have a CPU that has a separate memory, if that makes sense. So now you have two different pools of memory. And these are connected over a PCI Express bus. The issue with this is that the game renders to the memory that lives on the GPU. And I've tried to illustrate this with the sort of the width of the connection between these boxes, in that the bandwidth that the GPU has available to its memory is really high. Same goes for the CPU. And the thin string that connects these is not that fast. And you might think, okay, but that's fine. You know, we're just sending 60 frames per second. Like, we have gigabits of bandwidth. It's fine. We can send that. And that will be true. But the problem is that the game is hogging all these resources. So what the game is doing in order to sort of build these great virtualized cool worlds that we have today, it is like shoving all this data across this pipeline, streaming textures, streaming geometry. So that pipe is full, and if we were to start sending textures across this barrier, what we would do is we would stall the GPU. So the GPU would have to say, because it's a pipeline execution model, it would stop, pause, and then do our thing, and then go back to the game, which will sort of break the rule we talked about how to do this without having game performance impact. So the only way we can do this is, at the end of the day, the game is rendering it on GPU. So what if we could sort of say, can we point to the part of the memory on the GPU where the texture lives that we need in order to drive the hardware encoder? And it turns out we can. And there's a couple of ways of doing that on Windows. And I want to walk you through how hard this is to do on Windows, because of course, with Windows, there's just not one way of doing it. There's often more. So in order to do this successfully, the first thing you can do is use a tool called Windows Graphics Capture. The thing that Windows Graphics Capture does is, if you think about Windows, what Windows really does under the hood is it composites your screen using the GPU. So if you have like multiple windows, I might have like my Firefox window, and I have like my Microsoft Teams window, and then Discord. All of these are textures that live on the GPU. And then when there's time to sort of show them to the user, the GPU bakes them together, and you get that to the user. So what we can do is to say to the compositor, hey, please give me that texture handle, and then we can feed it to the hardware encoder. This is really, really good, and it's really, really fast, because again, we're sort of adhering to that GPU locality we just talked about. Problem is that this actually only works in later versions of Windows 11. It was available in Windows 10, but it didn't really work. So we have this problem where now we have only a subset of users. If you look at the device metrics, not that many people are on the latest versions of Windows 11. It's actually like the tail end of users, but there's a lot of people still out there on Windows 10. So this only works for a sort of subset of users. So to successfully do this for all users, we have to do something else as well. And that's where DXGI comes in. At the end of the day, what we can do is we can say, I want to capture the entire screen, which means we don't just get the game, but we get everything on the screen. And this works really well if the game is in full screen. If I don't have anything else I'm displaying on my screen, we can use DXGI to capture this texture. The problem is if I'm playing a game in, let's say, window mode, and I happen to have my bank details on the right, then I'm also sharing my bank details. So in order to sort of implement this correctly, you have to be super careful and track, like, when is a window occluding, what region do we have to crop, and as soon as you move a window, you also have to move the crop with that window. So there's a lot of application logic you have to build in order to make this happen. And then if you can't do that, I mean, what did we do before Windows Graphics Capture was a thing? Well, we had something called Video Hook. I won't go too much into this thing, but really what we're doing is we're sort of hooking into the game, and we're sort of replacing the draw calls. This is very, very, very not safe, but you can do this and capture the draw calls. The problem is that the way we're doing this is the same way people are building game sheets. So game developers are kind of killing this, and we think that this is going to go away over the next 5 years. And if you can't do any of these, you have to go back to doing it the CPU way. That's what we talked about before, where you sort of slinging it over the PCI Express bus. You can think of it as like spamming the print screen button multiple times a second. That's really what we're doing here, and it's really slow. We don't want to do this. So these are the 4 ways you have to just do to get the texture on Windows. But the problem is that you cannot just pick one of these, because during a session of streaming, the user might do different things. Like they might start the game in full screen, and then go to window mode, and then go back to full screen. So you essentially need to build something that can select between these and act as a frame pump, and sort of give frames on an ongoing basis, and figure out, depending on what the best possible capture method is to use, go up and down this ladder as you're doing things. Whew, that was a lot. Now we finally have a texture that we can use to encode. It's really cool. So let's just encode it. That would be easy, I guess. But nothing is easy on Windows. And the reason nothing is easy on Windows is because you have 3 different manufacturers of graphics card. And on Linux, you have access to things like FFmpeg, and there's great support for different hardware encoding backends. That's not so much the case on Windows. So in order to efficiently hardware encode on Windows, you can use, first of all, if you're using NVIDIA, using something called NVENC. It's a framework, been around for a long time, really good. There's a lot of tweakability, especially if you want to do low latency. I think this is the sort of industry-leading thing when it comes to hardware encoding APIs, in my opinion. Second, you have AMD. They have Advanced Media Framework. This is something that if you go back 5 years, maybe wasn't that good, but they've actually started to fix a lot of the bugs, and the graphics card they're shipping now can do AV1, and the quality, I think, is on par with NVIDIA on the later versions. So that's getting really good. Intel, if you have a small Ultrabook or like a thin notebook without a dedicated GPU, using something called Media SDK, thanks to Intel, they also deprecated that, so now we have to use one API. So if you built Media SDK, I'm not salty about this at all. At some point, someone at Microsoft saw this, and they were like, this is crazy. Like, developers have to build all these integrations just to get hardware encoding working. This is not the case for Mac, right? On Mac, it's one API, and you're done, called Video Toolbox. So they decided, like, we don't want to be worse than that. We're going to build something called Windows Media Foundation. And Windows Media Foundation is this tool that's sort of this abstraction that sits on top of all of these hardware encoders that you can use to say, I just want to do simple things, like I have an NV12 texture, and I want H.264 output that's hardware encoded. And then Media Foundation will figure it out, no matter what the hardware is. Cool, so we don't have to implement these 3. The problem is, as I was talking about before, in order to tune these encoders to do low latency and not make it look very bad, the thing is, like, Media Foundation doesn't expose those parameters that you might need to do those things. So you're kind of stuck in this land where you can either have an ease of abstraction, or if you really want the product to be good, you have to implement the underlying things. The same goes for codecs. If you want to use things like AV1, one of the things we did at Discord, we were super early about implementing AV1 in Discord. And the only way we were able to achieve that was by implementing the NVENC libraries and working directly with NVIDIA to sort of make this thing work. And the only way, that's the only way we could do it. So personally, for us, we can't really use Media Foundation. But that's okay. We only have to do 3 of them. So, we can just think about not doing against Media Foundation. Problem is now Qualcomm shows up to the party. And now you're thinking, like, what is Qualcomm doing here? Over the last few years, I think Microsoft has been trying to catch up to where Apple is on MacBooks. You have these ARM chips that are super power efficient, and Windows is like launching Windows on ARM, and one of their large partners in making these CPUs is Qualcomm. They're making the Snapdragon chip. You can buy them in thin Ultrabooks. The problem is that Qualcomm decided, we don't want to do a public SDK. You're out of luck. The way you have to do this is to implement Media Foundation. So now, as an app developer, if you want hardware encoding to work across all these platforms, you have to use all 4 of these if you want the control. So it's this crazy world where you have to, at least, if you want the full control, you kind of have to build all 4 of these. But I will say to you, if you're doing this from the scratch, I would start using Windows Media Foundation, because it can do a lot, and they're actually continuously improving it and making it better. So I would start with saying, what is the absolute I can push Media Foundation to? How far can I make this thing work? And if it turns out that I can't make it work, only then would I look at my analytics and be like, where's my users at? In terms of market share, I think NVIDIA has the most market share in terms of gaming GPUs, but it might be that your target audience or your customers are, for example, only using Dell laptops with an Intel chip. And then it makes sense to only implement the Intel SDK. So I would drive it as start with the thing that has the most amount of abstraction, and then build upwards to what you need and you think your customer needs and what your user needs. So that was only Windows. If you want to do this across multiple operating systems, you have to do it for something in Mac OS. You have something called Screen Capture Kit and Video Toolbox. And iOS, you have Replay Kit. I'm not going to read all this out, honestly. But the thing I'm trying to sort of convey here is that if you're making a desktop application and you want to do efficient hardware encoding and drive these extremely good hardware encoders you have on your chip, you have to, at the end of the day, implement some sort of matrix of these. But yeah, that's really what goes into hardware encoding things on Windows. There's just tons more I could talk about, and I don't really have time to talk about tons more, so I'm sort of going to leave it at that. The thing I wanted to sort of shout out before I go off stage is that another thing we're doing a lot of with Discord is we're trying to contribute to the open source movement when it comes to that. So one of the things we launched recently was a new protocol called libdave. Libdave is a way to do end-to-end encrypted audio video over WebRTC. Why do you need end-to-end encrypted audio video? You have to answer that question. But if you do need end-to-end encrypted audio video, we've open sourced a protocol called libdave. We've audited it with Trail of Bits, so it's cryptographically secure. You can find it at github.com/discord/libdave. I'm really proud of it. I think the team is really proud of it. But that's all I have for you today. Thank you very much.